Hello everyone, my name is Safianjum Borsha and I am here today representing a team of undergraduate students from Department of CSC at Prague University. Today I will be presenting our paper ID 226, titled Distinguishing Mainshocks from Foreshocks using Spatiotemporal Labeling and Interpretable Ensemble Learning. So, when a moderate earthquake strikes, the immediate critical question for both civilians and authorities is this a main shock or is this a foreshock? Signaling a larger imminent rupture. Misclassifying this can lead to catastrophic decision making, such as initiating rescue operation during a foreshock sequence instead of evacuating. For example, let's take the 2016 Kumamoto earthquake sequence in Japan. A magnitude of 6.5 event was initially perceived as main shocks, but a massive magnitude of 7.3 earthquake struck just 2 days later, significantly worsening the casualties because the worst was mistakenly believed to have passed. The core challenge in preventing scenarios like Kumamoto is that foreshock and mainshocks share indistinguishable waveform characteristics. While traditional stochastic models like ETAS provide long-term probabilities, they lack the precision for real-time individual event classification. Our objective was to create a robust, data-driven framework to bridge this gap. Utilizing gradient boosting ensemble models optimized via Bayesian methods. If you look at the methodology section, we built our framework using 88 years USGS earthquake catalog spanning from 1930 to 2018. All magnitudes were standardized to the moment magnitude scale to ensure uniformity. To train our model, we first had to define the ground truth. We developed a novel bidirectional spatiotemporal labeling algorithm. We defined a cluster for every event within a 50-kilometer radius and a 30-day window. An event was strictly labeled as main shock if its magnitude was greater than or equal to all neighbors in that cluster. Otherwise, it was labeled as a secondary event. So, when engineering the features, we strictly used backward-looking windows to prevent data leakage and ensure real-time visibility. We engineered several physics-informed features such as seismic rate, energy release, magnitude differential, and spatiotemporal gaps. When engineering the features, we strictly used backward-looking windows to prevent data leakage and ensure real-time visibility. We engineered several physics-informed features, such as backward-looking windows only to ensure real-time viability, and seismic rate, the frequency of event in last 7 days, energy release, cumulative strain proxy, magnitude differential, difference between current moment magnitude and recent local maximum, spatiotemporal gaps, time and distance since the last local event. To handle the time series nature of seismic data, we used strict chronological split training on the past and testing on the future to prevent look ahead bias. Missing values were handled using MICE imputation. Finally, we evaluated our classifier CatBoost, XGBoost, Light GBM, AdaBoost using Bayesian optimization to handle the class imbalance. Moving to our result, CatBoost demonstrated super sensitivity for safety critical detection. It achieved an AUC of 0.965 and recall of 0.97 for Mainshocks. In earthquake scenarios, high sensitivity is paramount. CatBoost distinguishes itself by minimizing type 2 errors or false negatives. This is crucial for ensuring a main shock is not mistakenly dismissed as a minor event. But we did not just want a black box model. We applied SHAP analysis to interpret the predictions. The magnitude differential relative to recent local history proved to be overwhelmingly dominant predictor. Furthermore, the model ignored static coordinates like latitude, longitude, and depth. This proves that our framework learned universal seismic dynamic rather than simply overfitting to specific fault lines. In conclusion, this study establishes that machine learning can reliably identify the role of seismic event immediately upon occurrence. By prioritizing the magnitude, differential, and local seismic history, our framework bridges the gap between black box ML and geophysical theory. Looking ahead, we aim to integrate this framework into real-time seismic monitoring pipelines and test it on specific fault zones. Thank you for your time.